Hi, welcome everyone. My name is Amit Saxena. I'm VP of Engineering at Mobile. This is today's agenda for my presentation. I'll have FPGA-based enterprise SSD controller design, a block diagram as to how one can design it, and then basically focusing more on the design challenges as to if you have to do SSD controller design in an FPGA, what challenges one needs to work on, and I'll get into details. And essentially the whole idea of creating this design into an FPGA is to address few challenges and try to use the reusable IP components, because IP components provide certain advantages instead of creating a custom design every time for every module. Given a block diagram where at a very top level showing that the IP components can be reused, I'll get into those IP components as to what features need to be there in the IP components and how integrating those components can create a SSD controller design, meeting those design challenges which I have outlined in the very beginning. And then the Mobile reference design, we have created a platform which is sort of a reference platform for a SSD controller design using Altera Arria 10 FPGA. And then I'll summarize in a couple of slides on Mobile as to what we do. So I'm going to be showing a block diagram for NVMe-based enterprise SSD controller design using Arria 10. So this is a block diagram. As you can see, it is using Arria 10 SoC. So it has got ARM Cortex A9, GPIOs, and the DDR4 controller. So this is the hard processor system. This is actually used to run some of the device firmware, which actually deals with some of the NVMe specific commands as well as the flash, because there are a lot of things which firmware has to do. And since it's a NVMe-based design, of course, you have a PCI Express hard IP. This is provided in the Arria 10 part. This is to provide the connectivity to the host running the NVMe driver. And then you have NVMe controller. This is again something which is IP component which sits in the middle. And of course, the flash-specific controller. Again, it is shown as sort of a block which actually has a lot of components within it to address flash. And the block diagram also shows some of the important paths, basically the data path. One you can see in the red essentially shows how data can be moved from some of the components in this design from NVMe to SSD to DDR4 and vice versa. You can see that there is a direct connect between NVMe, SSD as well as PCI Express. But since we have created this design on an FPGA, instead of using a soft IP for PCI Express, we are using the hard IP, which is part of the Arria 10. So this is a block diagram, and I'll get into the design challenges. The block diagram of the design was not a fixed design. It is something which is a reference design, useful to not only use this platform, do some optimization, do some software testing, trade-offs between some of the components in hardware to see the performance advantages, disadvantages. This is the challenge in terms of what exactly we are trying to address. So we are trying to be flexible to support different hardware configurations. So when I say hardware configurations, I'll get into details, but you can think of having some of the options available within the NVMe specification itself in terms of number of queues, multi-port implementation. Similarly, in the PCI Express, whether you are going to be supporting multi-path I/O, that would require you to have SRIOB, for example, with the various number of virtual functions you want to support. So those are the challenges. The design should be flexible enough where our customers or the end users should be able to pick those hardware configurable components and basically take it through the FPGA flow, do the testing, and then make it into a real product. And of course, this is we have done it on Arria 10 SoC, but ideally we should be able to port it to even within Arria 10 family, which has a bigger device, may not be an SoC. So it should be portable so that you can move design, SSD controller design across various technologies. And I talked about the customization. The challenge is to basically make sure that we do a design which can be customized based on various requirements. And of course, for flash, there is a major component which needs to run in software. For example, the statistics gathering, error recovery, reclaim, and other value-added enterprise SSD functions like endurance. We are working with partners who you might have heard about NV Endurance, where we can increase the flash endurance. So for that, the solution should be adaptable. It should provide hooks so that the additional value-added software can be integrated in the firmware which we provide along with our solution. The first challenge is the feature configurability. If you are familiar with the NVMe specification, even with various flash devices, there is a lot of configurability in terms of the feature set. Based on the flash, which device you are trying to target, you may have to correct certain amount of errors, which may not be sufficient to be handled by just the BCH. Because you are looking at an FPGA, the size of the BCH grows exponentially if you increase the number of bits which need to be corrected. So whether you can live with the BCH or you need to add LDP, this is one of the decisions we need to make, and when we created the design, we wanted to make sure that we can provide the option where one can choose between LDPC and BCH. And even within LDPC and BCH, one has to make a decision whether you are going to be doing it on a whole for a single data path or you want to do it on a channel basis. And again, that is a decision one needs to look at and decide based on what frequency one can achieve in a given technology. And of course, the number of flash channels, it has to be flexible, it has to be configurable, so the design supports how many channels you really want to support, the interface, what type of devices, whether you want to support just one specific device or multiple devices which can have interfaces, which can have a specific test mode command. This is one of the features. The design should be adaptable, configurable to allow that to happen in a system. I talked about multi-path support. This is again, your hardware component should allow you to have an implementation or our customers to have an implementation which is not multi-path I/O, but at the same time if someone wants, whether the design component, the IP component support it or not. So that is one of the feature configurability the design has to address. Vendor-specific command arbitration, this is one of the NVMe features. We want to make sure that our reference design allows that to be added in an implementation. Endurance support I talked about. This is one of the things which needs to be integrated, handled in hardware as well as software, so that we can provide APIs where value-added software can be integrated. NVMe Endurance is one example. Vendor-defined commands. This is also something which design should be able to support because it is value add, one of the differentiator for our customers to add vendor-defined commands. Number of IO queues and depth. This is one of the major things for the NVMe. The solutions are going to have varying requirement in terms of how many queues one wants to support, what is the depth, and design should be flexible enough to allow that configurability. So these are the challenges on just the feature, the specification defined feature. Then there are implementation challenges. This is something to do with the technology. Since we are doing it in FPGA, what frequency we can achieve based on what is the PCI Express bandwidth we are looking at. If it's a Gen 3 by 4, can we have a 128-bit 250 megahertz solution, or if it is Gen 3 by 8, we may have to go to 256 bits. That's going to make sure that you can accommodate the PCI Express bandwidth, but also you need to look at the size, because of course there is going to be increase in size if you go from one data path to another data path. Whether the design is going to be processor dependent or not, ideally it should not be dependent on processor or type of processor. And again, when we're talking about the SSD controller design, we need to look at basically verifying the design before we hit FPGA image on a board. So we need to interface with the third-party VIPs. In case of NVMe, you have some of the VIPs which you can actually use. So whether your design verification environment can be integrated with third-party VIPs. And similarly, third-party PHY IPs. In this case, it is Altera. So they already have a service integrated. The number of DMA engines, this is the implementation detail in terms of how many parallel commands you really want to have in a system. If you are familiar with NVMe, you can have as many commands as you want to handle. But in an implementation, one needs to look at how many flash channels one has and then decide how many parallel commands I want to have so that I can maximize the available throughput, available pipe on the PCI. Data path bit support, I talked about it. Again, it's technology decision based on how much bandwidth you need to handle, accommodate. The buffering. So the solution has to be optimum one, because if you look at doing a SSD controller design in an FPGA, majority of the area is utilized by the error correction. Error correction is big for the newer NAND devices which need 60-bit or more of error correction. The buffering has to be very efficient so that you are not going beyond the capacity of the device. And hardware-software partitioning, this is an implementation challenge. How many commands and what commands need to be handled in hardware, because that's what gives you the performance advantage, versus how many commands which has to be handled by the software because the hardware doesn't have that information. So this is one of the implementation challenge. and we have sort of defined as to what goes in hardware, what goes in software. So looking at these challenges, which are feature challenges, specification defined challenges, as well as implementation challenges, which are technology dependent, what our goal was and what we have done is to address all the features, looking at what variations are possible in the market and providing a reference design which can be customized. We do all the design, implementation and validation on our side, so that this is a sort of a proven design. Only thing one wants to do with this design is to sort of customize, target it to a device, add the value add software, and really test it, make it into a product. Of course, we have made sure that area and frequency are optimized so that you pick the right device, because these are the high performance FPGA devices and the prices vary based on which device you pick. And of course, the latency, bandwidth and QoS, these are the major requirements, and our goal is to make sure that these are met as per the desired performance requirements. So given the design challenges, we have, as I've shown in the initial block diagram, that you can actually do this if you have the configurable IP components. So I'll start with the NVMe controller. So we have UNH certified NVMe controller. UNH certification lab, if you are doing any NVMe product today, this is the place where you have to go and take it through the interoperability and certification process and get it certified. This is a public information. You can look at a product in the market and check whether the product is part of what is called as integrators list. So you can go on the UNH website. All the products which are available in the market today, if they pass interoperability and certification requirements, they are listed there. This IP is part of that integrators list because it has passed those requirements. And this is also very important because all the IP components need to have this minimal requirement that they are compliant and they are certified, because your end product needs to pass that requirement once you have that. So I have a block diagram of the NVM Express controller we have. The one thing which is good here is that this block diagram shows the multi-port implementation. So if someone has a multi-path I/O requirement, this is the optimum solution, where we have for each of the ports the unique register set, unique admin and IO queue which is required, and unique arbitration, because this is on a port basis, and the things which are common are just shown here. So you have the multiple threads. This is not really NVMe dependent. This is dependent upon how many flash channels you have. So this is shared across all the ports, because this is dependent upon your bandwidth in the system you want to accommodate. So essentially this is an optimized solution. Instead of instantiating multiple single port NVMe controller, you are having a one multi-port configuration which shares the DMA resources across all the ports. And then we are also having our own soft IP, because some of the implementations may not just be in FPGA. So we have again a PCI Express controller. This is PCI 6 compliant controller, and this is a pipe on one side, so we can integrate it with any of pipe compliant services in the market. We have basically the application interface which directly matches with what we have on the NVMe side. So this is again very optimum solution, low gate count, optimized latency, because we are not having any standard AXI, for example, interface here. And again, this is something which is Gen 4. It is available already, part of the PCI 6. And of course, DDR4 memory controller. In our FPGA implementation, we are using the DDR4 controller provided by the HPS, which is part of the device. But in ASIC implementation, or in some of the cases where requirements may not be met by what is provided by Altera's DDR controller, we can use our own controller. So this again provides standard interface AXI4. And on the PHY side, it is EFI 3.1 compliant, supports various QoS arbitration schemes. Three modes I would like to mention here, because this is again based on what is the target technology, what bandwidth you want to accommodate. You can go with the full rate mode, which is running at the same rate as the clock, the DDR interface clock. Or if you can't run at that rate, then you can bring down and increase the gate count, but you can still accommodate the bandwidth. So we have half rate mode as well as the quarter rate mode support. And of course, we have to have a lot of other configurability, which you can see in this block diagram. So we have this base controller, and a lot of configurability we provide by having the multi-port controller, where we can hook up multiple internal masters and provide the slave interfaces at the top of the memory controller. This is the most important part for a flash solution, and this is the SSD controller. Typically, if you look at in the industry, this is a very custom implementation. Every user, because of legacy, because of various reasons, This is not going to be sort of an IP. This is a custom implementation, and every design team is going to have its own sort of implementation, which they are always going to be biased with, because that's something which works. In our case, what we have done is we have taken a slightly different approach. We have created again a sort of a configurable SSD controller. It provides sort of a configurability which is needed for various requirements. At the same time, it also has some of the reusability components. So this is the block diagram SSD controller, essentially 4 major components. What we call as NCSQ, this is a NAND command sequencer. This is the main module which actually deals with NAND specific or the NVMe specific commands and convert them into flash specific commands. If you are familiar with FTL, this has FTL implementation in hardware. It also provides hooks, so that the implementations which have FTL in software can still be done. But our reference design implementation is actually doing FTL in hardware. So this is one of the unique things. Then we have the host interface which deals with NVMe data path. For SSD controller, as I said, that again an IP sort of still provides a lot of configurability built in. So NAND core sequencer, the heart of the whole design, it has FTL in hardware. It has all flash translation tables. We have various tables through which it manages the flash, forward translation table, reverse translation table, free block table. It manages all those tables, and then it provides the device firmware handshake, the API, which are needed for reclaim flash endurance. This is one of the major things, and error logging and other diagnostic features. So this is the main block which provides interface to the software. The FEMA module which you saw in the previous slide, this is the flash interface and media access. This is again comes to the data path. It does basically the striping and de-striping, because we need to have host data go to multiple channels to really meet the performance. So it is the block which actually uses 3 block table and does the striping on the right and de-striping when the read is happening. It manages pools of data like the hot and cold data, implements ECC. This is the block where we have the ECC implemented, LEPC or BCH. Flexibility is there to have single error correction block or per channel error correction block. And then there were 2 other blocks. Host interface, again this is pretty tightly coupled with how our NVMe controller works, but flash channel controller is again a standard IP component which basically manages the flash. And again this is an enterprise class flash controller. It is a micro sequencer based flash controller where we know that a lot of flash devices have their own test mode, and our users will have access to those test modes. Even we may not have access, but this controller allows more commands to be added transparently. We don't need to even know that. This is I think very highly sensitive and confidential information. So this controller allows those commands to be added by our end user, which has say NDAs with the flash vendor, without us knowing what those commands are, and still this is going to work. So this is enterprise class flash controller, which is defined to actually have very high throughput, independent command and response path. So this is board which we have created, which actually has this area 10 part, and as you can see, it doesn't have a lot of other components other than the DDR4 and some SODIMM sockets. And this SODIMM sockets are created so that we can have different flash we can actually test. Our customers can test by using the same reference board. So it can go up to 16 channels, and 4 terabyte of capacity can be there on this platform. This is SODIMM. Our customers would be able to not only change the parameters in the hardware, but also use different flash parts and do the test. So this is going to be available in a couple of months' time. So Movievel is a 4.5-year-old company. There used to be a company called GD Technologies, which was also founded by the same team, which got acquired by LG Infotech. We have been doing IPs in the past, and recently from PCI Express through NVM Express we are migrating towards or adding the flash, because the trajectory which is pretty, I think, natural to what we have done in the past, where we had interconnect experience, and with NVMe Express sitting or riding on top of PCI Express, we added NVM and now the SSD part, the flash. So there are 5 patents. We have filed in the flash storage and reliability. So it includes some of the LDPC specific patents. We are headquartered in Milpitas, and design centers are in India. So what exactly are the advantages? As an IP company, we are actually having these codes in the market for a number of years. There are parts in production using these components. So we have PCI Express customers, NVM Express customers. There are silicon using these components in the market you see today. And how we actually are able to provide these IPs successfully to our customers is by participating in all the consortium. Our focus is to get access to and participate into the definition of these protocols, so that once the specification is made available for general public, they already know what the specification is, they already have a solution. So we participate in all the consortiums, including NVMe, PCI, and we are an IP company. So our focus is to basically make sure that our end users or the customers are successful using our IP. And again, we are located in sort of US as well as in India, so we can provide support to all customers who are located in Asia or Europe. And again, we have to create sort of an ecosystem around the design IP. So we need to have participation or a relationship with third-party partners on VIP, on PHY IP, even in some of the cases, companies like NVM units. So we have created those partnerships so that our customers are actually not worried about how to integrate our IP into their own whole solution. And again, our goal is to have all the IPs which are not just a piece of software, vanilla code. We port these IPs into FPGA, take it through the certification process, get the code certified so that our users are comfortable using this code and they know that these are going to pass their product certification requirements. So these are advantages we have. I think we have been pretty successful having a pretty good customer base. Thanks.